sklearn, feature extraction, image-ingtograph. Description: the ingtograph function converts an image into a graph representation. The image is first divided into a grid of patches, with each patch representing a node in the graph. The edges between nodes are determined by the similarity between the patches, measured using a chosen similarity metric. This graph representation can then be used for various image analysis tasks, such as image segmentation, object recognition, and image retrieval. Inputs: image: the input image to be converted into a graph representation. The image can be in any format supported by scikit-image, such as a NumPy array or a file path. Mask: a binary mask that specifies the regions of the image to be included in the graph. This parameter is optional, and if not provided, the entire image will be used. Return as the format in which the graph is to be returned. This can be either adjacency matrix or sparsograph. The adjacency matrix is a dense representation of the graph, while the sparse graph representation is more memory efficient. Metric: the metric to be used for computing the similarity between patches. This can be any metric supported by scikit-learn, such as Euclidean, Manhattan, or cosine. Radius: the radius of the neighborhood to be considered when computing the similarity between patches. This parameter determines how many neighbors each node will have in the graph. Outputs: graph: the output graph representation of the input image. The format of the graph depends on the returner's parameter. Steps: divide the input image into a grid of patches. Calculate the similarity between each pair of patches using the chosen metric. Construct the graph by connecting nodes patches based on their similarity. Metrics: the quality of the graph representation can be assessed by its ability to capture the important features of the image. For example, a good graph representation should be able to segment the image into meaningful regions or identify objects of interest. Visualization plots: the graph representation can be visualized by plotting the nodes and edges, with the thickness of the edges representing the strength of the connections between nodes. Visualization tools such as Network X can be utilized to generate visualizations for the image graph. Fine-tune parameters: the radius parameter controls the density of the graph. A larger radius results in a denser graph with more connections between nodes. The metric parameter influences the similarity measure used to connect nodes. Choosing an appropriate metric is crucial for accurate graph construction. Uncertainty methods: the uncertainty in the graph representation can be estimated by examining the distribution of similarity scores between patches. Patches with low similarity scores are more likely to represent uncertain boundaries in the image. Challenges and fixes. Challenge 1: the choice of the metric can significantly impact the graph representation. Sample use case that resulted in challenge 1: using the Euclidean distance metric for images with different color distributions may lead to inaccurate similarity measurements and an incorrect graph representation. Fixes to challenge 1: experiment with different metrics, such as cosine distance, to find the best metric for the specific image type and task. Challenge 2: the radius parameter can influence the density of the graph, which may affect the performance of downstream tasks. Sample use case that resulted in challenge 2: using a large radius for an image with fine details might result in a very dense graph, making it difficult to identify important features. Fixes to challenge 2: adjust the radius parameter based on the size and complexity of the image to create a graph that is appropriate for the task at hand.